Okay, so in this lesson we're going to look at some of the ways that a function might not be differentiable and some of the things that go along with that. So if we have a situation where a derivative doesn't exist, remember the derivative is a limit of a slope. So now we just need to consider things where that derivative doesn't exist. And some of those situations on the graph might look like this. We have a sharp corner. And that is where the one-sided derivatives differ. Another situation, we could have a cusp, where the one-sided derivatives, one of them at least approaches infinity from one side, or negative infinity, and the other one either approaches a number or also approaches infinity. It's kind of like a extreme case of a corner. We might have a vertical tangent. And a vertical tangent exists when we are dealing with the slopes of a secant line or a tangent line approaching positive or negative infinity from both sides. And you'll see what that looks like in just a moment. And then there is also just a discontinuity. So if there was just your garden variety discontinuity, your removable or non-removable, that's going to stop a function from being differentiable for sure. Okay, so let's take a look at some examples graphically of what this might look like. Okay, so we're going to graph these functions and see if we can identify where the function is not differentiable. And I'm going to start with f of x, and I'm going to go ahead and do this in the calculator. So I'm going to go over to the num menu and select ABS for absolute value, and then x minus 2, and then off to the right we're going to do a plus 3, and then we're going to do a zoom standard on this, and you will notice that I've got the absolute value function graph, which we're not surprised by. This is an example of a sharp corner. Okay, this is an example of a sharp corner, and that's going to occur at x is equal to 2. That's where it seems like we have an instantaneous change in our slope, and I can just kind of point to that. I don't know if the cursor shows up on my screen or not here, but I've got the arrow pointing to the sharp corner right there. So how could I prove that with the one-sided derivatives? Well, sure. I mean, you could just kind of look at the slope, and the left-hand derivative, the slope of that is going to be -1. So the slope of anything to the left of that point will be -1. And the right-hand derivative, the slope will be +1. So that's one of those things that we can definitely show using left and right-hand limits. Okay, so now let's take a look at x to the 2/5 power. So let's clear this out, and x raised to the 2/5 power, and a graph of this. That would lead us to believe that this is a cusp, and that cusp is occurring at x is equal to 0. Okay, now how can we prove that this is going to be a situation where the derivative doesn't exist? Well, if we find the derivative using our power rule, we are going to get 2/5 x to the -3/5, and that simplifies to be 2/5x to the 3/5. So once we get that all set up, we can just say, well, if I go to try to find what g prime of 0 is, and plug that in into my derivative, we're going to get something undefined. Okay, so if that's the case, now we're looking at a problem, and we can see that the derivative definitely does not exist from an algebraic standpoint there. Okay, let's do this other one, this cube root graph, which is going to be kind of interesting. I think I can get that on the math menu. Yeah, there it is, option 4 on the math menu. So this is the cube root of x plus 2, and then plus 1, and we'll go ahead and graph it. And if I were to go to an x value of -2, I think you would see, watch the tangent lines, kind of pretend like you're affixing them. They're going to move along, and it's going to be a vertical tangent at x is equal to -2. Okay, well, how can I prove this with the derivative? Well, let's go ahead and do what the derivative is, and you'll see what it looks like. We will have h prime of x, and I'm going to go ahead and spot you the derivative. This one is a little bit challenging, but I think you could get to it if you thought about it enough. This is where that's going to end up at 1 over 3 times x plus 2 to the 2/3 power. Okay. Now, because this is one function acting on another, I'm gonna show you the goods on how to do this a little bit later. So you're just gonna have to trust me for the time being that this is how this works. Okay. And h prime of 0, actually not 0. 0 is okay. It's -2 we're worried about here. And if I go to find h prime of -2, well, once again, we end up being undefined. And that's going to be the reason why we can't find the derivative. The derivative just simply isn't defined there. Okay, let's move ahead here. You can do this activity here on this particular problem, compare the left and right-hand derivatives to show that the function is not differentiable at point P. Well, in order to do this, I'm going to turn this into a piecewise function here. And it's going to be the square root of x when x is between 0 and 1 inclusive. And it's going to be 2x minus 1 when x is greater than 1. Okay, pretty easy piecewise function to come up with. So if I go to do my power rule here, I'm going to end up with f prime of x equals... Okay, now we've got to think back to what happened when we took the derivative of square root x. If we're going to use our power rule, it helps to rewrite it as x to the 1/2 power. And its derivative will wind up being 1 over 2 root x. You can check it for yourself, but this time I can't include 0 on my derivative because that would be a problem, same problem as before. And then the derivative of the bottom rule is just 2. So if I go to find the left-hand derivative at, should be more complete there, x greater than 1. So if I go to find the left-hand derivative at x is equal to 1, I'm going to get a value of 1/2 because I'm going to put 1 right here into this function. And square root of 1 is 1, 2 times 1 is 2, so the denominator is 2, the numerator is 1, it's 1/2. And then the right-hand derivative at x is equal to 1. Well, there's no place to put in an x, so that derivative is just 2. Okay, so now that we know the left-hand derivative is 1/2, the right-hand derivative is 2, we can now make the conclusion that f is not differentiable at x is equal to 2. And that may be something that you might have to do on a test or a quiz, is to be able to do the one-sided derivatives and show that they're not the same in order to come up with the two-sided derivatives. Okay. All right, let's move along, shall we? Okay, this is another good problem right here. It talks about differentiability and continuity. And again, just like when it comes to continuity, sometimes if we find where a function isn't differentiable, it's either to establish where it is differentiable. So if you take a look at an x value of -1, there is a sharp corner. So we know the function is not differentiable at x is equal to -1. Okay? Kind of going backwards here, at x is equal to 0, there is a jump discontinuity. So therefore, the function is not differentiable at x is equal to 0. And now we have an x value of 2. There is a removable discontinuity. And that should tell us that we're not differentiable there either. Okay, so if that's the case, then I need to figure out where I am differentiable. And I want to point out that we've got an entire domain here of -2 to +3. So now that I know where it isn't differentiable and why, I can start to piece together all the intervals where it is differentiable. So we're going to start at -2 and go to -1, not inclusive. And then from -1 to 0, we're differentiable for sure. And then from 0 to 2, we're differentiable. And then from 2 to 3, and I'll put brackets on the endpoints there. And then lastly, we'll just knit this together with some union symbols that we know how to do. So those are all the intervals on which this function is differentiable. Okay. So let's go on to part B. Is there a spot where this is continuous but not differentiable? Yeah, at x is equal to -1. We are definitely not differentiable there. Let me do the green ink here because that'll make it a little bit more sensible for those of you watching the video later at home. Okay. And then the other question here, where are we neither continuous nor differentiable? Well, if you're not continuous, you're not differentiable for sure. And that's going to occur at x is equal to 0 and at x is equal to 2. So if you got those two things going for you, that tells you we are neither continuous nor differentiable there. Okay, moving ahead. There's a couple of important consequences of differentiability, one of which is that a good way to think of differentiable functions is that they are locally linear. So what does that mean? That means as you zoom in really close on a function, you are going to be able to see that it straightens out into a straight line. So let me illustrate what I mean here with this cube root function from earlier. If I were to use my Z-box tool, and I were to zoom in on around x is equal to 1. Okay, so I want to get my box tool, but I want to make it really, really tight. And if I were to zoom in like that, you would notice right away that the function sort of straightens out. So that's going to happen for differentiable functions, is that they are locally linear. And that's one of the reasons why we can use tangent lines to approximate values of functions at such close range to a specific x value. Now, another good thing to know is that if f has a derivative at any x value a, then f is continuous at that x value. Okay, now I'm going to put a star on this one. This is important because I can see down the road running into a question where we get told a function is differentiable. Okay, well, now you can make the assumption that it's continuous once you know it's differentiable. All right, a couple of other last things here that'll help on the calculator. If I want to find a numerical derivative on the calculator, I can do so. Now, I want you to think about what the idea of a derivative is. The idea of a derivative is we want the instantaneous rate of a change of some function f of x. And our goal was to put 2 points so close to each other that they were practically on top of each other, and that distance between them was so minuscule small that we could definitely find the slope between those 2 points and limit that distance down to nothing. Okay. Now your calculator is not going to go through the limit process. Your calculator instead is going to use the slope formula. But what it's going to do is it's going to put just enough daylight in between those 2 points that regardless, you could still find what the derivative is. Okay, so when it says use h is equal to 001 or 0001 here, no 001, and x is equal to 1, well, what the calculator is going to do, it's going to find f of 1.001, and it's going to subtract f of 0.999 because those are exactly 1,000th of a unit away from 1. Okay, so just as a quick aside here, if you were trying to find this for x is equal to 4, you would use 3.999 and 4.001 as your two x values. Okay, and then back in the denominator, you do 1.001 minus 0.999. Okay. All right, so what would we end up with here? Well, I don't know what the numerator would be, but I know the denominator is 0.002. All right, so I'm going to go to the calculator here and type in the function 2x squared minus x. So 2x squared minus x. And here's a little shortcut that will help you to do the numerator all at once. We're going to have the calculator do all the work. So to do this, I'm going to get vars, and then slide over to yvars and hit enter twice, and then type in parentheses 1.001. So what does that command do? It says, hey calculator, find out what y1 is worth at 1.001. And now I have to do the same thing for the 0.999. Okay, and then once I do all that, it ends up being 006. And then I think everybody knows if I divide those two out, I'm going to come up with 3. So 3 is my estimate of my derivative. And it's not going to be any different than the derivative at x is equal to 1. You find it with the power rule, you're going to end up with the same result that we did here. So the numerical derivative is actually not a bad estimation. It's just a little annoying to do, a theme and variation on the slope formula. Okay, now your calculator, just like Desmos, can graph derivatives. So why don't we see if we can graph the derivative of natural log here. And in order to do that, I'm going to hit the math button, and then I want to select option number 8 down here, which says nderive. So look at the calculator screen on the right side here, and it'll say nderive. So I want option number 8, and then it's going to be with respect to x, and I type in my function natural log of x, and then this is at x is equal to x, and I want to zoom standard because I messed with my window in the previous example, so zoom standard. Okay, and you might notice that this is the graph of the derivative of the natural log. And it looks suspiciously like 1 over x. Now, we don't get the whole picture there because there are some circumstances that are stopping us from being able to get that whole picture. All right, let's try this one more time for 1 over x. So I'm going to go back into this process, and I'm just going to change my function here to 1 over x. And we're going to hit the graph button, and there it is. And you will notice that this is the graph of -1 over x squared, which we're not surprised by that knowing what we know about the power rule, but graphically now we can kind of see the connection. It's 1 over x squared, but since we're in quadrants 3 and 4, that negative sign is what puts us back down into those quadrants with the transformation. Okay, folks, that wraps up our lesson on 2b, or not 2b. Have a good rest of your day.